So in this lecture we're going to look at several applications and models of exponential growth and decay. And as I mentioned earlier, since there is actually an easy model to model growth, viral spread growth, I actually did a short video on modeling the growth of COVID-19. And I'll just put it up there for anyone that's interested. It's certainly not mandatory by any means. So exponential growth. So like I said, if fire grows exponentially as long as there's fuel, disease grows exponentially, population can grow exponentially until, of course, it's arrested, till fire runs out of fuel, till something stops the population growth, like there's no food, etc. So this is going to be the general way that we look at exponential growth and decay. So we're going to say let y naught, so you can call that y sub 0, y0, or y naught. It's N-A-U-G-H-T. I think that is the spelling, and that's a British use. I've used y naught for such a long time, that's just what I say. Probably the first thing I was taught. So let y naught be the amount or number present at time t is equal to 0. So that's at the very beginning. That's before you start doing measurements. Then under certain conditions, the amount y at time t is modeled by this equation. So notice y naught is multiplied by the result of e raised to the k times t, where t is time, and k is some constant, which is usually determined by experimental data. So by PEMDAS, when you find y, you have to find out the value of e raised to the k times t first, and then you multiply it by y naught. Here's another important concept, doubling time. The doubling time is the amount of time it takes for a given quantity to double in size or value at a constant exponential growth rate is what we'll be talking about here, but it extends to any type of growth rate. So here's our first model. And again, calculators are used, but they're not necessary. And let me clip this little thing out right here, because the book does something here I don't really like at all. It's forgivable, I guess. I don't want to save this. I just want to clip it to the clipboard. So we're going to use this information to find the experimental value of k and then use it to do some predictions. I'm going to go ahead and give me some white space to work over there and then paste it. Okay, that will work. So now that I've got that here, let's go ahead and read the problem. So we're going to look, they're reminding us back in section 4.4, in a specific example, we discussed the growth rate of atmospheric carbon dioxide over time using a function derived from measured quantities taken from a table. So we're actually going to use a table of values in the formula y is equal to y naught times e to the kt to find an exponential function that gives the amount of carbon dioxide y in the year t. Use the model you produced in A to estimate the year t when future levels of carbon dioxide will be double the pre-industrial level of 228 parts per million. So here, what I'm going to do is we're going to set our start value at the year. This is going to be, I guess I can come over here, extend this just a little bit. So my start year, we're starting out with a value. So the year 1900 This is going to be our year 0. So this is our year. So basically it's called zeroing out. So the year 2000 is going, so this is the t value. So our year 2000 is going to correspond to 10 years that passed. And in 2075, 85 years have passed. In 21275 is 185 years have passed. And in 2275, it's 285 years have passed since our very first observation, which we're saying happens in 1990. And the other thing I wanted to bring out is this is the year 2020. So this is going to be predicted. This amount here is predicted. So is the amount here, and so is the amount here. So it has to be predicted from a specific formula, and that specific formula is given to be what we had before. Y is equal to y naught times e raised to the value of k times t, where our value t is time, not only time, but time in years. So let's go ahead and do this. If you want, you can change this to function notation. If you would rather write instead of y, f of t, that's completely fine. As a matter of fact, I like that so much because this is clearly a function of t. T is our variable. So our value of y naught is the amount we had that corresponds to y equals 0. So y naught, so our original amount at t is equal to 0, is 353. So our objective here, it's kind of like inverse and direct relations, ratios, what we did at the last of chapter 3. We need to estimate the value of k. So what we're going to do with that is we're going to use what we've observed. So we have observed values. These are actually measured. The book doesn't do this. The book uses future predicted amounts. But if you're going to predict them, you have to have a value of k. But we don't have a value of k, so we need to use observed values. So we're going to start with our formula. Y is equal to y naught, which is 353, times e to the k t. So I'm solving for k. That means I have a value of t. So I'm going to say in the year 2000, which has t equal to 10, the amount y of measured carbon dioxide I get from the actual table. And that is 375. So when I solve this, I can actually find the value of k. So once I find the value of k, then we're good to go. So this is 375 times some quantity. And I can put this entire quantity in parentheses if you would like. So what I'm going to do is I'm going to divide both sides by 353. And that's equal to e to the 10k. So the natural thing to do here is to take the logarithm of both sides. The natural log. Why the natural log? Because this is e. So that always tells you use the natural log. So let's take the natural log of the fraction on the left-hand side, 375 over 353. And I'm going to take the natural log here of e to the 10 times k. So again, I'm going to do this really slow and in steps. So the next thing I'm going to do is I'm going to simplify. There's nothing I'm going to simplify here, although I could, grab my calculator and figure out what this number is. I prefer just to wait to the very end. So using a logarithmic rule, the exponent here comes out to the top, and I have just the natural log of e. But the natural log of e is just 1. And remember, I'm solving for k. So all I have to do now is literally divide both sides by 10. And once I do that, I will grab my calculator and get an estimated value of k. The important part here is you saw the process that I used to get k. So doing that, bringing up the calculator, we will use parentheses here, and 375 divided by 353. Now that's going to be a number greater than 1 because the numerator is greater than the denominator. So I know the answer is going to be positive, and then I'm going to divide all of that by 10. And the approximate answer is 0.004. So here's the approximate answer, leading 0. And how many? I had 2 zeros. 0, 0, 605. And you could probably, it would be fine just to stop with 0.006. That's 6/10. That's 10 hundredths, 6 thousandths, 10 thousandths, 100 thousandths. We'll go ahead and use that. So that's my value of k. Right here is my value of k. So my original equation becomes y is equal to y naught, which was 353, times e raised to 0.00605. That's the value of my k times t. Now what they want us to do is to find the exponential function that gives the amount of carbon dioxide in the year k. So this is the example 1a. This is the function. And again, you could write this, and to be honest with you, since we are talking about functions, if it's not going to freak you out, the variable here is t. That's the independent variable. So I like writing f of t. But if you want to remember that f of t, just like f of x, is always equal to y, that's fine. So that's the answer to the first one. So then our next thing we're asked is to use this model to estimate the year t when the future levels of carbon dioxide will be double the pre-industrial level of 280 parts per million. So 280 times 2 is equal to 560. So we're solving for t here now. So my output is 560, and that's equal to 353 times e raised to this k value that we just found. So the next step again is I'm going to divide both sides by 300, not in 55, but 353. So I'm going to take 560 and divide it by 353, and that's going to give me the value of e. I hope you can anticipate the next move. We're going to take the natural log of both sides. Now I know that you could actually use the natural log property when you take the natural log of a quotient, but since we're going to be approximating this with the calculator, there's no real reason to do so. Again, we're solving for t. So if you recall from what we just did right before, this becomes the natural log of that fractional amount. And the exponent comes out in front. And then I have the natural log of e, which is just 1. So I'm not going to bother to write that. I wanted to write it down there for just a second. Now I'm getting rid of it because it's a factor of 1. So remember, now I'm solving for t. So now what I do is I divide both sides by that value. It's pretty nifty, right? Once you get used to exponential functions and their properties, they're really not hard to solve. So let's find out what year this is going to occur. And remember, our value t is to be added to our 0 year, which is 1990. Because remember, we zeroed out at 1990. So where's my calculator? There's my calculator. So let's figure this out. So the natural log of 560 divided by 353. This is going to be divided by, here we go, a really small number, 0.00605. I didn't put a leading 0 there. I didn't write down that leading 0, but that's okay, and I'm sure you can forgive me. And t is equal to 76.27 years. So when we add that to 1990, the year is going to be 2066 and some months into it. That's about 0.3, so that's about 4 months into it. 0.3 is, or maybe about 3 months into it, 4 months, thereabouts. Yeah, because there's 12 months, so yeah, it'd be 4 months into it. Okay, so there we have that one. Oh, here's one you'll like, because it has to do with money. Money's always perks up people's interest, which is, I mean, it's good, but, you know, math is everywhere. We live on the Space Coast. Could you imagine, or do you think we could be shooting up these SpaceX rockets if we didn't have really good math to help us out, to calculate the window, the launch windows, etc. So remember, that's our amount, our total amount in the bank when we invest a certain amount of money called the principal at a certain rate over a certain time. So how long will it take for money in account that accrues at an interest rate? So R is equal to 3%. Remember, we need to turn that into a number, so you can turn it into a number by dividing by 100, or if you wish, you can take the existing decimal place and move it over 2 places. So that's tenths, 100ths. This is 3 100ths. That's my R. So how long will it take for money in an account that accrues interest rates of 3% compounded continuously to double? So what is it that's going to double is the principal. So the money original investment is P. So we want to know when our amount is twice that original investment. So my amount is twice that original investment is equal to P E, and here we're going to go ahead and just use 0.03 T. And again, our unknown T is our unknown. And our unknown is in years. So it's important to know that it's in years, it's not months, it's not in seconds. So again, it's always kind of helpful to remember, because these kind of freak you all out, use PEMDAS parentheses. You're going to do this first. So it's okay if I divide both sides by P. So that's going to give me 2P divided by P is equal to E raised to the 0.03 times T. Now before I do anything else, I'm going to go ahead and simplify the left-hand side, and the principal is non-zero, so I can cancel out 0. So I got 2 is equal to E raised to the 0.03 times T. And what's our procedure for solving for T? We take the natural log of both sides. Then we use the exponent rule of logs to bring the 0.03 T out in front, and over here I have the natural log of E, which is 1, and now I just simply solve for T. So T is equal to the natural log of 2 divided by 0.03 T. So think right here in your head, how long do you think it's going to be? If my T value comes out to be 1/2, I know I've done something wrong, right? Because it's not going to double in 1/2 of a year at that interest rate. So I'm thinking anywhere around 10 to 20 years. If I'm getting 50 years, I know I've done something wrong. So again, let's grab our trusty calculator. It's an interesting question. How would you ever know if your calculator is wrong? We just literally trust our calculator. Since I'm not for sure exactly the rules for parentheses on this particular calculator, because like I said, this is Linux, and who knows who wrote this program and what rules they did. I do want to do this though. Can I go back? I'm going to put my leading 0 there, just for you all's benefit. So it looks like what I have here. I'm going to hit the equals. So yeah, so that's 23.10 years. And I guessed anywhere between 10 and 20 years. And 23.10 is not too far off. So it would take 23 and 0.10 years. So that's 0.10 times 12, because there's 12 months in a year if you want to convert the 0.10 to months. So again, that's not so bad, and it's a financial calculation you may wish to do sometime. and verify financial calculations on your own. So example 3. So here we're given in function notation. According to the U.S. Census Bureau, the world population reached 6 billion in 1999 and was growing exponentially. By the end of 2010, the population had grown to 6.947 billion. The projected world population in billions of people T years after our zeroing out time of 2010 is given by the function f of t is equal to what you see there, meaning right here. Based on this model, what will the world population be in 2025? So really for this one, it's not difficult at all. The only thing to remember here is to recall that our zero, we zero out, that's the verb I'm using, at 2010. So that means the year 2025 corresponds to a value of t equal to 15. So I've been given a function, so I want to find the function value at 15. So this is just pure calculation. We used to call it, I don't know if you all call it this now, just plug and chug, because you have all the numbers, you've been given a formula. You just have to find the remaining amount. And again, I'm going to tell you to use, in these cases, PEMDAS parentheses here. You should calculate this first and then multiply it by 6.947. So that's what we're going to do using the calculator. So I'm going to write e, and then x to the y, and then I'm going to put in parentheses 0.00745, sorry I didn't use the leading zero, times 15, close the parentheses, and hit equals. And then that amount I'm going to multiply by 6.947, and the end result is 7.768. So f of 15 is equal to 7.768. And what was this number? This number was in billions. So it's in billions people. It's a lot of people in that period of time in 2025. You know, that's just 5 years away. So now our next question is when will it double? So using the exact same method that we did before, we have what's the current population in FT is equal to, just redoing that here, 6.947e raised to that 0.00745t. So when will the population double? So the current population, the zeroing out population, refers to the 6.947. Remember, that's my y naught value. So that's 2 times 6.947 is equal to 6.947 times e raised to this junk up here. I'm not going to bother to write it down, because the next thing I'm going to do is I'm going to divide both sides by 6.947. And when I divide both sides by that, I just get a 2 on the left-hand side. So that's 2 is equal to 0.00745t. And this is exactly the method I take you through in the lecture about COVID growth and doubling time. So I take the natural log of both sides, and when I take the natural log of e raised to this exponent up here, what it does is it allows me to take that exponent and put it in front. And what is left behind? The ln, the natural log of e, which is 1. So now I'm good to go. And it's very similar to just what we did. I have the natural log of 2 divided by 0.00745. Remember right here, in case you forget, that's what I'm solving for, is that variable right there, t, is equal to t. So again, get our calculator out, do clear. I'm going to find the natural log of 2 in parentheses divided by 0.00745. That's going to malformed expression. Well, I guess I better do it right? Natural log of 2 divided by 0.00745. And that gives me 93.04 years. So t is equal to 93.04 years. And let me write out years. And we add that to 210, because that was my 0 year. We'll just round it off to 0. So this is going to happen in 2103. I'll be long dead and gone. And some of you might not actually be alive either. It depends on how old you are here and what we do in science to make us live longer. Then finally, it's just another variation on this theme. If this trend continues, when will the world population reach 9 billion? So again, our unknown, t is our unknown. And once we find t, we have to remember to add it to the year when we zeroed out, which was in 2010. That's given in the problem. So the total is 9 billion. So since 6.947 in the original formula, given right here, is also in billions, don't change these to billions. Just put it down as 9. 6.947e times this exponent up here. And that's that value right here. So again, this is in parentheses. So what I'm going to do is I'm going to divide both sides by 6.947. And then that's going to be equal to e raised to the and I hope you anticipate what's going to happen next. We've done it several times. I'm going to take the natural log of both sides. And when I take the natural log of the right-hand side, using the log properties, I come up I put one too many zeros in there. So again, all I do now is I'm going to divide both sides by that number. And in doing so, that gives me the value of t. I'm just being really lazy here today. I don't feel like, I'd rather erase than to rewrite. Although, got a new, oh there we go. I've got a nicer keyboard down here. You can't see it. I'm not actually using the laptop's keyboard. That's my value of t. So what I was trying to do is figure out which buttons to push. I'm just messing up everything, right? For some reason, it's my function. Okay. At any rate, let's do this. It turns out, now I've overdone it, turns out that t, once I do the calculation, we'll go ahead and do the calculation again together. There it is. I'm going to take the natural log of 9 divided by 6.947. And then I'm going to divide that by 0.00745. That gives me 34.8 years. And we add that to our zeroing out year, which is 2010, to get the final year of year 2044, almost the year 2045. If that trend reaches, the world population, can you imagine this number, is 9 billion. A lot of people. Of course, as it turns out, that trend may not continue as people have access to birth control in first world countries. Then the birth rate is going down, and it just depends on whether that trend continues. So here we go. Not every exponential model requires an amount to be increasing over time. We also have decreasing functions. So if our function f of x is equal to b raised to the x as an exponential function, where b is greater than 0 but less than 1, then the function is decreasing. So we can also use those types of functions as models. So we have decay function models. So the half-life is the amount of time it takes for a quantity that decays exponentially to become half its initial value. So suppose we still use the same model, we still use that same initial formula, but in this case we're going to discover when we're taking the natural log of the fraction, that the fraction is actually amount greater than 0 but less than 1, and that's going to indicate, wow, we are decreasing here. So suppose 600 grams of radioactive substance are present initially, and 3 years later only 300 grams remain. Determine an exponential function that models this decay. So we're finding the k value again. So we're starting off again with that same model. Y is equal to y naught times e to the kt. And in this case, t is equal to 3. Y naught is how much we have initially present, which is 600 grams. What do we have 3 years later? That's the amount y. We have 300 grams. So we have to find the value of k. So let's plug and chug. 300 is equal to 600 times e to the 3k. So I'm going to divide both sides by 600. And 300 divided by 600, as I said, is going to be 1/2. So what I'm going to do now, I'm going to take the natural log of both sides. So the natural log of 1/2. Before we were taking the natural log of a number that was larger than 1. Now we're taking the natural log of a number that is less than 1 but greater than 0. So that leads to the natural log of 1/2 is equal to 3k. So the natural log of 1/2 divided by 3 is equal to k. So let's find out what that k value turns out to be. Grab the calculator. So we're going to do the natural log, and I'm going to go ahead and put 0.5 for 1/2 divided by 3, and k is equal to, notice it's negative now. That shouldn't surprise you, because the natural log of a number less than 1 is going to be negative. So k is equal to minus 0.23. So we found the original equation, which we need to write now. Y is equal to the original amount. So y is equal to y naught times e to the kt becomes y is equal to 600 times e to the minus 0.23t. So now I've got the equation I can use. So I've done A. Use the function from A to calculate how many grams remain after 6 years. So all I have to do is plug in t is equal to 6. Which remember, I mean, that would be, if y is equal to ft, I'm finding f of 6. So again, remember, PEMDAS requires we do this first. And with a calculator, we do e raised to, in parentheses, minus 0.23 times 6. It's going to give me, it should give us a really small number, and it does. And then we multiply that by 600. Wasn't a super small number, but the answer is 100. Let's just round that to 151. It's approximately 151 years. And depending on how accurate you keep the value of k, remember we rounded off the value of k at the tenths rather than the thousandths, we're going to be slightly different here. In my notes over here, when I did this earlier, I got 150.04, not years, sorry, this is grams. That's how much we'll have left. I got 150.04 grams, but that's because I used a full value of my k. In other words, I may have just kept it in the calculator, and that does make a difference. It's called rounding errors. And I'm going to give you all a break. For example 5 and for example 6, I'm not going to do them. If you all go into physics or chemistry, you'll have to do these on your own. But, you're doing this at home, and these are pretty involved calculations. I don't see myself giving you something like that on the exam. If you can just do everything up to example 4, you'll be fine, and I will check the homework to make sure. You should be able to do example 5. So, example 6 is a bit more than I care that you do. It's really not hard, and it's very fascinating. If someone wants me to do it for you, you just let me know. I've already got it done in the lecture I made last year, but for this year I'm giving you all a break, and I'm not going to require you to know it.